We saw last time that as a consequence of the completeness of the number system, if you ever have a set of integers, I almost said real numbers, woo. If you ever have a set of integers that is non-empty and bounded above, I'm looking for it, non-empty and bounded above, then that set of integers must have a largest member. If you stand on your head and write this proof, you will see that whenever a set of integers is non-empty and bounded below, then that set must have a least member. I'm now going to address a remark that is to a small number of people. Will everybody else just forgive me? Suppose you are working only with positive integers. If you take a set of positive integers, it's automatically bounded below. That's for everybody. So therefore, every set of positive integers, if it's non-empty, has got to have a least member. If you ever have any set of positive integers, any subset of the set of all positive integers, if it's non-empty, it's got to have a least member. Now, what is the special property of an order that says that every non-empty subset must have a least member? This is being directed at 3 people. Right? What do we say when you have a total order and every non-empty subset must have a least member? The order is a well order, right? For 3 people, right? Everybody else, I beg your forgiveness. So what we're actually seeing in this position is officially with the completeness that the ordering in the set Z plus of positive integers is what is called a well order. Kind of important in a certain context that will not rear its head right now. Okay. Now the set of all integers, which is traditionally written Z, the set of all integers cannot be bounded above, because we know that in order for any set of integers to be non-empty and bounded above, it's got to have a greatest member. This non-empty set of integers doesn't have a greatest member, therefore it cannot be bounded above nor below, right? Okay. Now I'm going to tell you something else. I'm going to add in something here, and I'm going to say smallness, it's a weird heading, of the numbers 1 over n for n in Z plus. Strange heading. I'll tell you what I have in mind. Suppose that we are given a number p that is greater than 0. Greater than 0? Positive. Okay? If you see less than 0, you say negative. If you say greater than 0, you say positive. If you use the word positive at any other time, you've made a mistake. If you use negative at any other time, you've made a mistake. Don't ever say negative when you're subtracting. I know that the world is full of people who look at a little minus sign, it's the operation of subtraction, and they use the word negative. They should all be making fries at Wendy's.
Are you positive about that?
She couldn't resist it, right? So anyway, I could say almost, but that would be okay. Now, suppose that p is greater than 0. We are going to see that there exists something an integer n, actually, I'll even say a positive integer. I was going to say in Z plus, but let's say this. Such that, you know the word such that, it says, not only is it going to be an integer, it's got to be a very special kind that's going to do a special job for me. That's what such that means. Listen, I've got to actually harp on this. I've had some of you write, choose an upper bound W of set S, such that x is less than or equal to W for every x in S. It's ridiculous. If you say choose an upper bound W of the set S, if you know that one exists, you can say choose, then it is automatically true that the inequality x less than or equal to W will hold for every x in S. Not such that, it's already there. You see, such that is used to add an extra requirement. You see? You could say choose an upper bound W of the set S such that W loves to eat ice cream. That would make sense. I may not particularly think it's wonderful for the proof, but, it depends. Okay? All right. Suppose that P is positive. We are going to see that there exists a positive integer n such that the number 1 over n is less than P. This is what I call smallness. I'm going to tell you that numbers of the form 1 over n for n a positive integer can be made as small as you like. That's what I mean. I'm going to draw you a picture. Here's a quick and dirty picture. Here is the number 0. That's what it looks like. And here's a bit of number line. 2 inches is too much. It's going to run off the screen. 1.5 is plenty. Okay? And I'm going to show you the number 1 over n. And let's get a bit of number line. And now let's put about, here we are. And here's P. Given any positive real number P, we are going to see that there exists a positive integer n that is, if you like, large enough to make 1 over n small enough to be underneath P. Okay? The method of proving that something exists is to give an example. So let me tell you how to get an example. Using the fact that Z plus is unbounded above. Don't we know that at this stage? If Z plus were bounded above, it would have to have a largest member, and that would be trouble, because if you take any integer, you can always add 17 to it and get a bigger one. Okay? Well, using the fact that Z plus is unbounded above, what is the information that I have in my hands? Z plus is unbounded above. I know that something exists. Isn't that right? So when something exists, you can say, choose an integer. I'm going to choose an integer that is really, really big. Choose an integer n that is so big, thank you so much, Mark, that is so big that it's greater than 1 over P. How do you know that we can choose an integer greater than 1 over P? Well, P is not an upper bound of the set of integers, is it? It's not an upper bound. Because this number, I'll tell you what, I'll put under my breath here, using the fact that Z plus is unbounded above here, and therefore that 1 over P can't be an upper bound of z plus. You see? That's what I had in mind. See? We choose a member of z plus an integer greater than 1 over p. Okay? Well, observe that we have an example. I'm going to lead my unicorn in through the door now. I've got in my hands a certain integer n, and n is greater than 1 over p. Observe that 1 over n, by the simple rules of inequalities, will be less than p, and that's the end of this whole topic. You see? If you ever have a positive number p, 1 over p cannot possibly be an upper bound of the set of integers. Using that information, when a number fails to be an upper bound, what can you say? Number is not an upper bound. What does it mean when a number is an upper bound of a given set? It means that every member of the set is less than or equal to your number. See? What does it mean when a number fails to be an upper bound? Yeah, there is at least one. See, if I say everybody in this room can speak French, the denial says at least one person in this room doesn't know how to speak French. Okay? I can prove that theorem. So anyway, using the fact that 1 over p is not an upper bound of the set, which gives me the information that there exist members of that set that are bigger. When something exists, you can say, choose. Choose an integer n greater than 1 over p. And in my pocket, I have an example of an integer n, a positive integer that's obviously positive, is greater than that. And it's a positive integer n satisfying this inequality because it satisfies that inequality, and we're done. And we're now going to do a little topic called the denseness of the set of rational numbers, and I want to tell you what this is about. So I'm not going to leave all the stuff from the text here. I'm going to tell you what I have in mind, and you can look, you can read. Oh, I've got news for you. I got about a dozen letters from Cambridge University Press this morning and last night. Our textbook is now on order, and they are rushing it. I don't know, it makes me think of an old quote from the great TV show Yes, Prime Minister, that probably none of you have seen.
What do you mean, ration?
Well, that's what I mean. The description there was that when a letter came into the Prime Minister's office, they sent back a reply saying that your letter is under review or your letter is under active review. Under review means we've lost your file. Under active review means we're trying to find it. I don't know. I don't know what it means by rushing. Maybe it'll take a week. I don't know. I really would like you to have a hard copy. It is my experience that many students, if they can't get a book on the first day, somehow I've got into a kind of routine without it, and I don't know what you will do. I've told the bookstore that I have no idea what the students will do or what they'll want to do, particularly because there's an on-screen version, but some of you will want it, and at least it will be there. So I just thought I would mention, if I get news from the bookstore that it's in, I'll put it on the contents document immediately. Okay, now let me tell you what I want to do. I'm leaving out all the chit-chat, it's in the text. Incidentally, one or two people have been using very old versions of the text. Am I right that the computers in the science building somehow reach the on-screen version of my text? So somebody was talking to me this morning. Who was it? Was it you? What did you see there?
No, I have a copy on a flash drive of your text, but I can't update that on the school computers. So
Oh.
you can't download it to the school computer.
But if you were to install, can you not install onto the flash drive from one of my CDs from the beginning of term?
I could on my own computer, but the school computer won't let me. So that's why I just said I'd have to.
I'll also suggest something else. If I give you the URL, you might be able to copy that directly into your flash drive and then in there run it and install and just direct it to install into the flash drive. In other words, don't go to program files x86, okay? Except you go to program files x86, right? Everybody, there will be a new version of the text sometime tomorrow morning. It may not affect most of you, but the most recent version at present is February 3. I think 3, 5. Yeah, there will be a February 11. And there is something in the set theory chapter that I've made easier and so on. So anyone who is doing or has done the set theory, you will definitely want this. All right, now let's read what we're going to be doing here. Suppose that A and B are real numbers. Any real numbers, A less than B, given. Picture A to the left, B to the right, okay? I am going to tell you why this symbol, by the way, a Q in bold symbol like this, is the standard symbol for the set of rational numbers. Okay? I'm claiming that there exists a rational number that is in the open interval running from A to B. When I say that this set is non-empty, I'm saying that there exists a rational number, a member of Q, that is between A and B. What I'm saying is, whenever A is less than B, there must exist a rational number somewhere between A and B. We could call this the sardine theorem, that the rationals are packed into the number line like sardines, tightly packed. So this is what we're going to see. And the nature of this proof is as follows. I'm telling you how I'm going to do it. I've got to actually swing a butterfly net at the rationals and catch one that is between A and B. And I'll tell you how I'm going to do it. I'm going to take a very, very large integer n that was going to be the denominator. You know what a rational number means? It means a fraction. An integer divided by an integer. I'm going to do it with a very, very large denominator. And if I take a really, really large denominator, then when you when you increase the numerator bit by bit, the rational will creep very slowly up. You know, if you take a zillion for the denominator, then you could take 5 over a zillion, 6 over a zillion, 7 over a zillion. It's hardly moving, you see? And what I'm going to do is I'm going to move bit by bit, increasing the numerator slowly, 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 and I'll catch one of these little guys in between A and B. Now I want to tell you a little better what I mean by very large. So I'm going to take a very, very large denominator. I'm going to tell you how large. I'll start writing now. We choose a positive integer n such that 1 divided by n is less than b minus a. You say, what the hell is that? Look here. Look at this picture. B minus a is the length of that black stick. It's the distance that you walk from A to B. I'm choosing a denominator that is so large that 1 over that denominator is less than the distance that you walk from A to B. How do you know you can do this? I've just done it with you. If you like, you could say choose a positive integer n greater than 1 over b minus a. You can do that, and then 1 over n will be less than b minus a, if you like. Or you can use what I did with you a few minutes ago. You see? Now I'm going to try to catch a rational number with this denominator, and I want to catch it between A and B. So I'll tell you what I'm going to do. I'm going to say, let's look at all possible rational numbers with this denominator, and let's see which ones are bigger than A. You know what I want to do? I'm going to look at all rational numbers with this denominator that are bigger than A, and I'm going to try and come down as close as I dare to A in the hope that it'll be underneath B. That's my idea. So this is how we're going to do it. We define, and I'm going to define S to be the set. I'm trying to get an equal sign. I'm going to define S to be the set of all, let's make this a bit bigger. I'm going to define S to be the set of all integers m for which something happens, for which the fraction m over n is bigger than a. I'm looking at all possible numerators of fractions with a denominator n. All my fractions that I will ever work with in this proof are going to have the same denominator n. What is n? N is the integer I chose over here. There is the end of my sentence. That's why I chose n once and for all for this entire proof. You won't ever see me say anything about for all n, will I? For every n, or choose n or something. No, n is a fixed particular number that I've already chosen. Now I'm going to look at all possible rational numbers with this denominator n, but bigger than a. On the face of it, it doesn't seem to be obvious that there are any of these little guys, does it? I mean, who knows when that will happen, if ever. But immediately I'm going to rewrite this. I'm going to tell you that this inequality, remember n is positive? If you multiply both sides of the inequality by n, do you understand that this statement is exactly the same as that one? The set that I'm calling S, I've expressed as the set of all possible numerators of fractions that are greater than a. I'm rewriting the same set. It's exactly the same as saying the set of integers m for which m is greater than na. And I want to tell you something. Since the number na, by the way, I have no idea whether that's an integer or not, and I don't care. All right? Since that number is not an upper bound of the set of integers. How do you know? How do you know that this number is not an upper bound of z? There are no birds to fly, right? The set of integers does not have an upper bound. So if you take a number, it can't be one because there are none. Okay? Since NA is not an upper bound of z, we know that S is not empty. Can't be empty. There are some examples of integers greater than NA because NA is not an upper bound of z. You understand? I would also like to mention, note please, that S is bounded below. Isn't it? Isn't S bounded below? I'll prove it to you, but I'm not writing a thing. The number NA is a lower bound of the set because all the members of the set S are greater than Charlie over here. You understand? Therefore, that number is a lower bound. See? The set S is bounded below because in front of my nose, I'm looking at a lower bound of that set. Then the set S is also non-empty. Now, what do you know about any set of integers that is non-empty and bounded below? When you have a set of integers and it's non-empty and bounded below, what can you say? Given any set of integers that's non-empty and bounded below, it's got to do what? It's got to eat breakfast. Why? It's got to have a least member, right? If a set of integers, if the members of a set are always integers and the set is non-empty and bounded below, it's got to have a least member. So it's not just you can talk about an infimum, or you can do a jolly sight better than that. I can say that this set has a what you call a minimum, right? A least member. So I'm going to make a definition. We define. Never use the word define unless you are saying exactly what you mean by something. We define M to be the least member of S. There is a least member, right? So you can do that because a non-empty set of integers that happens to be bounded below always has, you want to go look here? You wrote this one. When you have a non-empty set of integers and is bounded above, it's got to have a greatest member. And then I said, I should have said, didn't I? I'm sure I said turn it upside down and do it. A non-empty set of integers that's bounded below has a least member. The text says that. All right. Now, where are we? I'm lost. We're over here. We define M to be the least member of S. Now, let me tell you something. I know that M over N is greater than A. How do I know? It's because M belongs to S. You see, it's one of the members. M over N will be greater than A. Do you understand? And I know that M is the least possible integer that you can divide by N and be greater than A. You understand? So I know that if you take a smaller positive integer, and this is the one I have in mind, that's less than M, is it not? And you divide that by N, that can't be greater than A. Not greater? What do you know about a number that's not greater than A? I'm talking about a number. If a number is not greater than a given number A, less than or equal to. You can't say it's got to be less than. See? Is less than or equal to A. That much I know. the number m over n, here it is greater than a. And m minus 1 over n is not more than a, is less than or equal to a. Now, in this picture, I've drawn m minus 1 over n as if it were less than a. But it might by accident be equal to a. I do not care. Okay? Now, what I'm trying to help you see is that this rational number, this fraction, m over n, I'm going to show you is trapped in the interval running from a to b. That's what I want to tell you. Well, it's certainly greater than a, is it not? So I'm going to tell you something. Finally, give me a moment. Finally, note that if you take this rational number, m over n, you can express it as m minus 1 over n plus 1 more over n. Can you not? Now, m minus 1 over n can't be more than a. You understand? But 1 over n is less than... Let's come underneath. 1 over n is less than what? B minus a. You see? And this is equal to b. So I got news for you. M over n is below, is strictly less than b. It's bigger than a. Where did I say that? And it's less than b. Gotcha. Trapped it. See? I managed to catch myself a fraction between a and b. This is actually a sneaky little proof. You need to write this 3-4 times and say it before you will have it straight. Okay? Please take careful note of that thing. And as a general story, I want to say to you, that that your most important activity in a mathematics course, and it's nothing to do with this course. I say exactly the same thing if I were teaching, which I'm not, if I'm teaching trig. You take the material that you get in class and you redo it to make it yours, to make yourself the author of it. You may be explaining why cos squared plus sine squared equals 1. Don't tell me, I've come into this course and all of a sudden, for the first time in my life, I'm seeing proofs. Not true. Not true. You know, proof is explaining why things work. If all you're ever doing is memorizing, you're going a quick way into a padded cell. You can't do math that way. So I want to tell you something. Before you give me a moment, and then I'm coming to both of you, that if you want to be able to write a proof, the first thing you need to do is be able to rewrite the proofs I give you and put yourself as if you were the one who was explaining that proof, and make it that you forget that I exist and that you've got it, that you are the author of it. Plagiarize me. See?
I like something you said to me earlier.
Yeah.
This isn't what I was going to ask about, but earlier you said know it as if, make sure you know it so well that you could give a talk on it.
So that you could give a talk. Yeah. That's the way. Jonathan.
The last proof you wrote at the very end, you wrote m over n equals b. It should be less than.
M over n
equals something which is less than or equal to something else.
is equal to this number. And here's just another way of writing m over n.
Right, but you're saying m over n is less than a plus b minus a.
And the a plus b minus a
Is b.
equal to e.
So this number is less than something that happens to be b.
Right, but it looks like the way you have it written that m over n is equal to b.
No, it doesn't.
If we had it
Because it's less than something that is equal to b.
The implication
So
is it's
now,
together.
if there's any single strict less than sign in that block, then it finishes with less than. Yes, sir.
The title above this proof is
Yeah, there's a chit-chat in the text which you're going to read. Denseness of a set means, given any two numbers A and B with A less than B, you can catch a member of the set between them. That's what it means. And that's what you're going to read. I removed it from your notes because I accidentally pasted in too much from the text, and you're going to go look at it. Okay?
I had something else.
Yeah.
About this proof we just did. Can you turn it on so you have it?
Where's it? Here.
Yeah. Wait, first we define S to be members M of Z.
To be the set
Set of members
of integers m, yes,
following with a certain.
inequality.
But then you said we define M to be the least member of S. So
That's
M
right.
is any.
So first we defined S. And there's the end of my sentence. We defined, there, end of sentence. Now using this S, which is now in my proof, I'm defining M to be the least member of S. So M is an integer. It's one of the integers in S. It's the least one. Because M is a member of S, this inequality holds.
I guess I was just confused by using the same. It seems like you're using the same symbol for different. One's arbitrary, one's a specific.
No, nothing arbitrary.
Okay, because
First I've defined S. S is a specific set of integers. Now I'm now referring to that particular set S that I have defined. And S means nothing except the particular set I defined. Now we're defining M to be the least member of that set S. That's the way it works.
So it's once we have that period, the M is
And
just arbitrary.
and M is not arbitrary. It's the least member of the set S previously defined.
I guess
That's what it
just
is.
because you used M in the definition of that set.
Ah, yes. Yes, I suppose I could have used a different letter like K. It even occurred to me, and it's been my experience that the students don't like it when I do that. But if you've used M for the dummy in there, then you shouldn't use the same letter M for the least member. There could be a logical problem there, but at this level, I usually find my students prefer the same letter.
And not.
But to be honest, a different letter of the alphabet is healthier there. I don't want to go there now. But you're right. You're right. Okay, so now I want to tell you something. In calculus, I'm going to ask you a question. Never mind this course. In calculus 1, let's talk about something. If f of x tends to infinity as x tends to a, and g of x tends to the limit 4, as x tends to a, then what do you think we can say about the limit as x tends to a of f of x plus g of x? Never mind any kind of rigor or anything, think Calc 1. If the one function approaches infinity and the other one is tending to 4, what about the sum?
Towards infinity.
You believe this? I mean, for values of x close to a, this is very, very big, and this is about 4, so it's not more than 3. Excuse me, not smaller than 3. You see? So, reasonable, that's going to infinity. And if I change that, if I don't put 4, if I put a minus 3, it's still true, right?
Infinity minus 3.
Yeah. So I want to point out to you that it seems reasonable, in view of Calc 1, it seems reasonable to define infinity plus 4 to be infinity. Yeah? And infinity minus 3 to be infinity, to bring an infinity symbol into the real number system. You see? We're actually going to do this. By the way, what else do you think we have in Calc 1? What should infinity times 7 be? If one function tends to infinity and the other one tends to 7, what does the product do?
Just infinity, just a lot
Yeah.
faster.
Yeah? 7 times faster, right? This should be infinity. What do you think in Calc 1? Think Calc 1. What should infinity times minus 7 do? Well, if one function tends to infinity, going up to infinity, and the other one's going to minus 7, for values of x close to wherever it's going, you've got a large positive number times something roughly around minus 7. The product is negative, and it's going to minus infinity. Do you understand? So if you want to put an infinity symbol, you've got to put a minus infinity symbol. Okay? Very well. Think Calc 1. What do you think infinity times 0 should be?
It's indeterminate, and I have no idea.
If one function is tending to infinity and another one is tending to 0, the product?
Seems like it should be 0, but as you get closer,
Seems
it
like, I don't know.
does it
Let's have a look.
converge?
Wait a minute. I want to change color. Let's look at the limit as x tends to 2 of, and I'll take the absolute value of x minus 2 times 1 over the absolute value. The reason I'm putting absolute value is so I don't have to get any headaches with pluses and minuses. See? Right. Who knows this limit? What is the limit as x tends to 2 of x minus 2? That tends to 0. By the way, the second factor tends to infinity, right? The product tends to 1. So maybe these question marks, maybe I should put a 1? Well, maybe, but what if I change this and put a 5 here? Now the limit's 5. Yes? I got news for you. I can make it anything. I can make the limit not exist. I can make it wobble. I can do something with a sign. Make it wobble. You see, the product of infinity times 0 should not be defined because it doesn't fit the rules, the limit behavior that you see in Calc 1, right? What are the other things that we don't want to define?
Infinity divided by infinity.
Here are some other bad ones. Um, 0 over 0.
Infinity over infinity.
Anything over 0, actually, right? Infinity divided by infinity.
Infinity power 0.
Infinity minus infinity. Isn't that a bad one?
Yeah.
These are the ones that in Calc 1, Calc 2 are called, and you use the word, indeterminate. And that's when you use special techniques. One of those techniques is this theorem called L'Hopital's rule that students love and professors hate, that you learn and you use in Calc 1. You know why professors don't like it as much as students like it? Because it's a very clumsy way of doing many problems, very often by being a little bit street smart, you can get it much more quickly without L'Hopital's rule. But the students don't want to be smart, they just want to grind it, you see, without having to think. So students like L'Hopital's rule more. By the way, who invented L'Hopital's rule?
I'm guessing not L'Hopital.
It was not L'Hopital. He stole it, actually. He actually took lessons from somebody named Bernoulli. I'm not sure, was it Johann Bernoulli? There were a couple of Bernoullis. And although L'Hopital was a fairly good mathematician, the Bernoullis were better. And he took lessons from one of the Bernoullis. And then he wrote a calculus book. And he proudly put this theorem in his calculus book, but it was taught to him by Bernoulli. Bernoulli was not pleased. Anyway, I just wanted to mention to you that we do introduce symbols minus infinity and infinity into the number system, and we introduce an arithmetic up to a point, okay? We don't define everything. We certainly don't define infinity minus infinity.
Zero divided by infinity?
0 divided by infinity should be 0. Infinity to the power of 0 is in trouble. Yeah, that's another one. That's another one.
To the power of 0.
And 0 to the 0 could also be in trouble. Absolutely.
Anything to the 0.
Yeah. Not anything. 5 to the 0, it's got to be 1.
Almost
See?
anything to the 0 is 1.
Yeah,
Zero
well,
is almost anything.
Yeah, so.
So 0 to the
So,
0.
but listen, folks, there's also an inequality. A real number is always understood to be less than plus infinity. Okay? But greater than minus infinity. Would you please have a look at the text here? Okay? I'm going to say to you, please take a brief look at the text on this. Just a little bit of chit-chat about introducing those symbols. Do we need those symbols? We do not. But they shorten the statements of a number of theorems later on. Okay? So I just wanted to mention this. Now I want you to be very careful to see what it is that we do. There are exercises on the Archimedean property of R. Can you see I've removed that? And the only other thing that we're doing is we're going straight across to the extended real number system, throwing in the infinities. Okay? I'm walking away from this chapter now, and we're going to spend a little bit of time together introducing the very beginnings of something that comes in chapter 6. Gone. Chapter 5. Out. And I want you to consider the system of real numbers. And if the system of real numbers was like a bunch of candies or buttons or some whatever in a bag that you could shake, I don't think we could have a theory of limits and continuity and derivatives and integrals. But the real numbers are not thought of as piled into a bag, are they? How do you think, how do you picture the real number system? A line. It is the fact that real numbers are strung onto a line that gives us a flavor, a geometric flavor, allowing us to consider that certain real numbers are closer to one another and other real numbers are further away from one another. Is that reasonable? What is it about the real number system that strings the numbers onto a line? Let's think what we know about the real number system. What the real number system provides us with the set R of numbers. Two special members called 0 and 1. The plus and the times, arithmetical operations. what the algebraists call binary operations, if you want to use fancy language. And the less than. The real number system consists of 6 things. No, equals just means same object. The real number system consists of 6 things. The set, the special numbers 0 and 1, the plus and the times and the less than, subject to a bunch of facts, commutative rule and distributive and associative and all the stuff, you know, all the rules of arithmetic and the rules of inequalities. What rules of inequalities? That the less than is a total order. If A and B are 2 numbers, maybe A is less than B, maybe B is less than A, maybe A is equal to B. One and only one of those conditions holds. And if A is less than B and B is less than C, guess what? And you know what else? If A is less than B and you add x to both sides, A plus x will be less than B plus x. You know these rules? All the stuff of inequalities and arithmetic. And finally, one last cherry on the top, the axiom of completeness. Now, I could possibly have taught you a chapter 5 that would take up the whole of this course and then some, simply just deriving the ins and outs from some basic rules of arithmetic and inequalities and completeness. We could have done a much more extensive chapter. And I could do something even more extensive. I could say, why is there such a system? How do you get it? And that would be a whole course. An entire course. And guess what? It will be a second course. It requires a first course in set theory, and most of you have seen no set theory at all, even if you think you have. And so what I'm actually saying here is we're in a position where we're at a certain level with the number system. We've made a compromise. We've got some information. We've learned how to do certain things. We even know that between any 2 different real numbers, you can find a rational. We know a few things, okay? We know that every non-empty set of integers, if it's bounded above, has a greatest member. We know a few things. Done a few exercises, some of us, huh? Okay. Now, among the various equipment that comes along with the number system, what is it that gives the number system its geometric flavor? Is it the ability to add and subtract and multiply? Definitely not. It is the less than sign. It is the less than sign that strings the numbers onto a line and makes it feel that some numbers are closer to each other than other numbers. Actually, I could define for you a distance between numbers. You know how you get the distance between a couple of numbers? Definition of distance. Subtract the smaller from the larger. If you've taken the same number twice, by the way, subtract any one from any one, you get 0. See? The distance between any number in itself should be 0. If you take 2 numbers that are unequal to each other, the distance is the bigger minus the smaller. If you're not sure which is bigger and which is smaller, you know what you do? You subtract any way you like and put, what's this? What am I doing? Absolute value, right. So anyway, the moment you think about closeness and farawayness, you are introducing an underlying structure that enables you to talk about limits and continuity and derivatives and integrals and all the good stuff of calculus. The underlying properties of any kind of system or space, as we like to call it in mathematics, that make farawayness and closeness meaningful in some sense or other, is called the topological structure of the system. The heading of chapter 6 is called Elementary Topology of the Real Line. The real line has a topological structure. We're going to investigate it. At a slightly deeper level, more advanced than our course, you could look at the topological structure of this plane, of R2, the plane. I want to tell you something, that in the plane, there is a perfectly good sense of far away and close by. The plane is not strung on a line, is it? It's kind of, it's got, well. But I want to tell you something, that if you take 2 points in the plane, we can define a distance between them. The most common definition is to take whatever they do in pre-calc. You know, you take a square root of something squared plus something squared. You know what I'm talking about? You make that the definition. You see? And then you've got a bit of a headache. You've got to explain that this distance does certain things that distance is supposed to do. I'm not going there, you see? And that would give you a sense of closeness and farawayness in the plane. You can do it in 3 space. Actually, you can do it in k-dimensional space for any k. And actually, none of those are really where the action is. You can do it in infinite dimensional spaces. And you know what? You can even do it in spaces for which dimension doesn't even make sense. And those things are called metric spaces. And in an even more advanced setting, one day you let go the metric. It's like an old story. 2 people are asking, the story dates back to the year 1800, and I don't know, 1870, 1880, I don't know. 2 guys are sitting in a coffee shop, and one says, "How does the telegraph work?" And the other one says, "I'll tell you. Imagine that you have a very, very long dachshund with its head in Vienna and its tail in Paris. If they pull the tail in Paris, it barks in Vienna." And the other one says, "Ah, so. But how does the wireless telegraph work?" He says, "It's exactly the same, but without the dachshund." That's the old story. The underlying limit structure, topological structure of a system are described as coming from close and far away ideas, you see. And what seems to be underlying this is a definition of distance. In the plane, you can make it the definition, that distance formula. By the way, that's not the only important definition. There's other things you can do in the plane. I'm resisting the urge to tell you all kinds of good stuff. But in the line, the distance between numbers is the bigger minus the smaller, right? So now what I want to say to you is that if you, let me just see how I'm doing. Okay, I'm doing all right. If you look at what I've been saying, it seems to be dependent on distance. Actually, you can do it without distance. You can get rid of the dachshund. It is possible to describe in an even more abstract way the minimal structure that you need to make limits and continuity and derivatives and integrals and all that good stuff meaningful. And in that bare bones setting, you are dealing with something called a general topological space, which is way, way, way beyond the scope of this course. You can't do that until you have finished 4382. not 4381. You have to do 4382 before you can do that stuff, you see. And so I'm letting you know that we are just having the just tiny little beginnings, looking inside the number line to see exactly what it is about the number line that makes limits possible. What's all this big deal about limits? Well, I have to tell you something. The initial glimmerings of calculus came from a gentleman by the name of Jonathan Lewis. No, what was his name? Archimedes. Archimedes. He was known as the person who discovered all kinds of scientific principles and mathematical ideas. May have been the greatest intellect of antiquity, of known antiquity. And effectively, he is the originator of calculus. I wonder if you could close the door. And Archimedes' idea bore a lot of fruit in the 16th century with a notation that was developed in which the initial calculus ideas of Archimedes reached a point where you could use them practically to describe motion of planets and all the rest of it. And it was very, very exciting. But unfortunately, some of the wonderful ideas of Archimedes had begun to evaporate, and people were working in a very sloppy way. And I've told you that at the end of the 18th century, in approximately 1790 something, you know, French Revolution times, you know, this. An English bishop, I've told you this, named George Berkeley, wrote an essay rebuking the mathematicians, saying, you know better than I am. In the year 1801, a German mathematician by the name of Bernhard Bolzano came up with the definition of a limit, and for the first time wrote a logical basis for setting up calculus in a way that could make sense. This limit idea, I've told you the whole story. I've led this all the way to Bertrand Russell's paradox. If you think you're getting the whole story again, forget it. You've heard it. Just play the video from the first lecture. But in order for limit to make sense, you need to have an underlying, what we call topological structure. You see? Right, I'm going to give you just one little definition, and that's as far as we're going. Suppose that you've got a real number called x and a set u of real numbers. Don't have to use a u. I know I've usually used an e or an x or an s or an a or a b. Anyway, doesn't matter. I've got a set called big U of real numbers. Now you understand that if x is a real number and u is a set of real numbers, it may be that x belongs to u and it may be that it doesn't. I'm not interested in that. I'm interested in whether x belongs to u with brass knobs on. I want to know whether x belongs to you, and belongs, it so much belongs that it's buried deep inside you. And I'm introducing a brand new word for you. And here's the new word. A number x has to be an extra specially good member of you, called an interior point of view. That not only does it belong to you, but it's a special extra good kind of member. An interior point of view, if it is possible to find, you know what possible to find means? There exists a positive number delta in such a way that if you start at x and you walk to the left by delta and you walk to the right by delta to make a stick. You see that stick running from the number x minus delta to the number x plus delta. There exists a positive number delta such that this stick will be a subset of U. It didn't say for every delta, it said that there exists one. For every delta would be kind of crazy, because if you said for every delta, that would include delta equals 55 million. If you went to the left by 55 million and to the right by 55 million, you've got one whopping enormous blue stick there, have you not? The chances of this being included in a given set called U is kind of, they talk about the snowball in hell, right? You're not saying for every, you're saying it is possible to find. You know what that means? That if you make the number delta small enough, must be positive, that the blue stick, if you make that blue stick short enough, then it'll be a subset of U. You understand? This is the opening step to the topological structure of the number line. Definition. A number x will be called an interior point of a set U. Not only does it have to belong to U, but an interior point if there exists a positive number delta such that the blue stick that you see over here is included in U. The blue stick is the open interval running from x minus delta to x plus delta. I want to tell you something, and then I will stop, I promise. This stick is usually, we give a description, we name it. We call it the stick centered at x with radius delta. The stick center x radius delta. Guess what you do? We're not doing it in our course. It's too advanced for us. Well, what would you do if you were working in the plane? You would say a point in the plane is an interior point of a set U when what? There exists delta greater than 0 such that the disk, open disk center, your point, radius delta is included in U. And guess what it would mean in three-dimensional space? You would say a point is an interior point of some set U when there exists delta greater than 0 such that not sphere, there's a special word for the solid thing, ball. When the open ball center your point, radius delta, is included in the set, you see. Oh, forget about 3 space and 2 space, too hard. That's green stuff. We're doing yellow stuff. We're doing the baby stuff here, you see. Okay, well, next time we meet, and I have no idea when that's going to be, maybe it won't be snowing on Monday the 17th. I don't know. The 17th is Lincoln's birthday. Who knew that? I knew it. I wasn't born in this country. But anyway,